So good afternoon, everyone. It's a pleasure to have here our friend Alberto Saldaña, a common visitor. He's from Instituto de Matemáticas of UNAM in Mexico City. And he's going to talk about, from competing species to nodal solutions of the Yamabe problem with connections to wolf packing, right? Yeah. Okay, so thank you again for coming.
Thank you, Hugo. It's always a pleasure to be here, and I'm very happy to share with you some of the mathematics I've been doing in the past 3 years. So the point of my seminar is going to link 3 concepts. As Hugo was saying, the competition between species. For example, we can picture 2 or 3 or L species of wolves fighting. Then what does that have to do with the Yamabe problem that we are going to define and talk about? And then what is the link between, one of the ways we're going to link these 2 concepts is with something called the optimal partition. So let's try to understand these 3 concepts. Okay, so as I was saying, with nodal solutions of an equation called the Yamabe problem that has a link with the Poincaré conjecture, this is the starting point of the seminar, optimal partitions and species fighting. So let us start with the Poincaré conjecture. This is the very famous problem stated by Poincaré in 1904. It was solved by Peterman in 2002, and the statement of the problem was basically this: every closed and simply connected 3 manifold is homomorphic to a 3 sphere. The problem, in fact, can be generalized, and it was a surprise for me when I was preparing the seminar to learn that it's not completely settled. So I just took this part from the Wikipedia stating the generalized Poincaré conjecture, and it says that if you have a manifold which is a homotopy sphere, then if one fixes a category which can be topological or piecewise linear or differentiable, then what you want to know is if every homotopy sphere is in a chosen category is isomorphic to a standard n sphere. Okay, so stated in this way, there are some cases where it holds and some cases where it doesn't hold. If we are looking at topological manifolds, then it's true in all dimensions. For piecewise linear, it's true in all dimensions except in 4, and in 4 is equivalent to the differential case. And in the differential case, it's false in general. First known counterexample is in dimension 7. Then there are some dimensions where it's true, like 1, 2, 3, 5, 6, 12, 56, 61. In fact, so dimension 4 is unsettled. All odd dimensions are okay, and all even dimensions between 6 and 62, they are also okay, but then it's conjectured that after 64, it doesn't hold, but it's not known. Okay, so the Poincaré conjecture is a big problem that has inspired many mathematicians to create new methods and try to solve the problem. And one of these mathematicians was Hidehiko Yamabe. He was trying to solve the Poincaré conjecture, and his approach to the problem was first to simplify a little bit the situation, the structure of the manifold. So he stated this problem and gave a solution. Given a closed Riemannian manifold of dimensions bigger or equal 3, there is a conformal metric G prime, which means that I am going to get this G prime from the original metric by just multiplying it with conformal factor, which is just a positive function. Yeah, here, which is just a positive function, such that with this conformal change, the new metric is going to have constant mean curvature. So this was a first approach of Yamabe to try to simplify the problem, and from there try to solve the Poincaré conjecture. He gave a proof which ended up having some mistakes, but then the mistakes were solved by Trüdinger, Aubin, and Schoen in a series of papers. Well, although there was a mistake, and the mistake that Yamabe did was a problem with the critical exponent that we are going to see in a moment. Working with the critical exponent is delicate, and this was the source of the problems in the proof of Yamabe. But other than that, the question that Yamabe raised has motivated a lot of research and a lot of methods, and there is a lot of mathematics thanks to this conjecture. Okay, so the thing is that if you are trying to find this new metric with constant mean curvature, you can restate the problem in terms of a PDE, which is nonlinear, which is this one. Here we have a PDE on a manifold. This Laplacian is the Laplace-Beltrami operator on the manifold. This is the scalar curvature of G, the scalar curvature of G prime. And if you have a solution to this nonlinear problem, then you can build a conformal factor that will make your Yamabe problem. No, this will have, whenever I multiply this rho with my original G, I will find a new G prime that has constant mean curvature. So, thank you. Yes, this will be better. Thank you. So, okay, the point is, if I can solve this equation, I can solve Yamabe problem. And from the PDE perspective, when we see an equation that is very well motivated, what we want to know is everything about it, no? Like, how is the set of solutions? How can we characterize solutions? How do solutions look like? So now this is going to be our goal, trying to understand the equation as much as we can. And the first step is to simplify the equation. So for example, let us now consider just the sphere. And we are going to fix the two mean curvatures as already constants. And let's try to understand all the set of solutions, or as much as we can, of the solutions of these equations. So for example, some questions would be, are there positive solutions, which are the ones I need for the conformal factor? If so, how many and how do they look like? How far can I push the analysis to understand them? And what about sign changing solutions? No? Once I understand the positive ones, can I do a similar analysis for sign changing? How many? How do they look like? And there have been several papers and approaches and methods trying to solve these questions. So one important thing to say about this equation is that it has what it's called a variational structure, meaning that we can associate an energy functional, and critical points of the functional are going to be solutions and vice versa. Solutions are going to be critical points of this functional. So in this way, working with the functional is going to characterize all the solutions of the equation. And the energy functional looks like this. So we have the L2 norm of the gradient, an L2 norm of a V, and the L2 star norm of a function V. So where is my energy functional defined? We're going to look at this in a Sobolev space where I'm going to ask for the minimum in order to get my energy functional well defined. So this is the set of functions in L2 so that this term exists, so that the gradient is in L2 so that this exists. And I don't need to ask integrability here because in fact, it turns out that this space is embedded in L2 star. So we get that for free. It's borderline. It's just a continuous embedding, but it's embedded. So we don't have to worry about integrability. So now, what's so special about this critical exponent? Let me tell you a little bit of important aspects of the problem with the critical exponent. One is the relationship with the stereographic projection. So stereographic projection is a way of relating the Euclidean space with the sphere without a point. And it works more or less like this. So a point in the sphere will be mapped to the Euclidean space in a one-to-one correspondence. Now, it turns out that the critical exponent relates very well with the stereographic projection because of the following. If we define, so sigma is going to denote the stereographic projection, and we define psi as this function here. Then for any function C infinity in the sphere, I can define a function B in Rn with this formula. So U composed with the inverse of the stereographic projection. So it's taking someone from Rn to the sphere, and then I multiply it with this factor, with this explicit factor psi. If I do this construction, then I can relate the Laplacian from this nonlinear equation that we saw earlier, which we will call the conformal Laplacian, with the usual Laplacian in Rn. Okay, and then here appears a factor, which is this exact psi with this critical Sobolev exponent, which, let me write it here. Oh, no. So just to keep in mind that 2 star is 2n over n minus 2, and n is the dimension of the manifold. So you can see that in order to have this well defined, my n needs to be bigger or equal to 3. Okay, so this is one thing about the critical exponent. So in particular, if I look at the equation that I was trying to solve and to understand, and I apply this composition, this construction with the sigma in terms of the V that we constructed in the previous slide. So composing it with the inverse of the stereographic projection, multiplying it with the psi, we see that the left-hand side gives us this factor, and the right-hand side also gives us this factor. And it's a positive factor, so I can cancel them. And we see that this equation and this equation are going to be equivalent. So solving a problem in the sphere now is equivalent to solving a problem on the Euclidean space, which is flat, and maybe it's a little bit simpler. Well, we'll see. So the problem in Rn is also variational. So now I can define an energy functional in a suitable Sobolev space, which now doesn't have an L2 term. So we have here the L2 term of the gradient and L2 star of the solution. We have this term here has vanished into in this transformation. So where do I look for critical points of my functional? In a space that has the minimal requirements. So I ask for L2 star integrability and L2 of the gradient. Yeah, sure.
This side that you constructed, if you rescale it, you still understand the question still the same?
What do you mean rescaling it?
So instead of dividing by 1
yes.
plus norm x squared, you divide by 1 plus lambda and norm x squared. The equation still looks like the second equation here.
Okay, yes, we're going to look at invariance under scalings in a moment. Okay. Yeah. So the next thing about important things about the critical exponent is that it is invariant under some dilations. So as we were saying, this space embeds into the LP. And now the two terms in my energy functional are the L2 norm of the gradient and the L2 star norm of the function. So if I take a function U in this space where my energy functional is well defined, and I construct a dilation in this sense. So I scale the variable and I multiply by a suitable term, then the L2 norm of the gradient and the L2 star of this scale function remain invariant. So this is the problem when we say about that this embedding has compactness issues. It's not compact. And why it's not compact? Well, because you can have a sequence of functions here whose norm in this space always is bounded away from 0, but that can converge pointwise to 0. Why is that? Because when I rescale a function in this way, I have a process like the one pictured here. This part here makes everything concentrated in one point. And then this point here, which has a negative exponent, tells me that it's going to be blowing up at that point as epsilon goes to 0. Okay, so dilations make my energy functional invariant. And this is a source of lack of compactness for problems with the critical exponent. So now that we have understood a little bit of the things surrounding the critical exponent, what can we say about the set of solutions of this problem? Well, let's look first for radial solutions. Well, if I look for radial solutions of this problem, they solve this ODE. And then using ODE techniques, we can solve this problem with these explicit functions, which are called the bubbles. And in fact, we can show that these are all possible radial solutions. So they are all positive, and there are no sign-changing radial solutions for this problem. Yes, it's when delta is 1 and psi is 0. This is the psi. And we call these solutions the bubbles. So now we were using this ansatz that the solution was radial. So what about if we ask for a general positive solution? Then we can use the theory of elliptic equations that tells us that all positive solutions of this equation have to be positive and radially symmetric. Have to be positive and radially symmetric. So all positive solutions are radially symmetric. Then by the ODE techniques that we mentioned here, they all have to have this form. So in this way, we have characterized all the solutions of the problem in Rn. And now we can go back with the stereographic projection to the problem that we wanted to solve on the sphere. Yeah. This one?
Yeah.
All positive solutions are radially symmetric. Yeah, this is the moving plane method. The way one shows this is called the moving plane. Okay. So then all solutions of my equation on the sphere are going to have the shape of the solution that I would have under this construction that I did, that was establishing the link between these two equations. So we have characterized all positive solutions. Now we can ask, what about sign changing solutions? Are there any? We already know that we won't find radial solutions, but maybe we can find other type of sign changing solutions. So the problem why we don't have radial sign changing solutions is because of this result that is solved using an inequality called the Pohozaev inequality, telling us that there is no solution in star-shaped domains. So this equation here with Dirichlet boundary conditions will never be solved in balls, which tells us why there aren't any radial sign-changing solution of the problem in Rn, but also in nothing that is star-shaped, meaning that there is a point that connects any other point with a line. So also not in things like this, where I can connect things. So this also tells us, for example, that there won't be a positive solution in a half space. So maybe someone would have tried the idea of considering a half space, building here a positive solution, and then just reflecting it. This won't work because you will never find a positive solution in the half space. Okay, so finding sign-changing solutions is not as easy. So one way of approaching this problem was introducing symmetries that will help you manage the lack of compactness. So this was suggested by Ding in 1986. So let us consider functions in the sphere that are O of m times O of n invariant. What does this mean? This means that if I have an element in the sphere that I can embed in Rm times Rn, because m plus n equals n plus 1, and this has to be bigger or equal 4, well, then my function only is invariant under the set of symmetries that remain, that keep unchanged the Euclidean norm of each of the entries of a vector in the sphere, where, let's say, Z1 belongs to Rn, Z2 belongs to Rn. If I change Z1 and Z2 for some other element that has the same Euclidean norm, then my solution is going to remain, my function is going to remain invariant. So Ding introduced the symmetries. One can think that with these symmetries, the function now only depends on two real variables, which would be these Euclidean norms, but in fact, it only depends on one, because we are in the sphere. So the sphere additionally relates these two Euclidean norms. So we have the symmetries imposed on the function and the symmetries imposed because we are in the sphere. The final product of all this construction is that solutions or functions that have the symmetries are one-dimensional. So they are not radially symmetric. Well, we are in the sphere, but they only depend on one parameter, and this one parameter can be, for example, expressed like this. All right, so with the Ding construction, we reduce the complexity of these elements to just things that are one-dimensional. So we can now consider the Sobolev space of all the elements that have this symmetry. And the magic of doing this, this construction with the symmetries is that we gain the compactness of the embedding of the sublet space in the L2 star. So now we can minimize because we know that we are going to arrive at something that is different from 0. Well, with this construction, with this compact embedding, Ding showed that the problem has infinitely many sign-changing solutions. Exactly. Now you cannot concentrate in one point because of the symmetries. The concentration will have to go not just in one point, but in a lot of in a very large orbit, and this cannot happen. No. All right. So how does these solutions look like? No. What about if we try to imagine how this would look in R3, for example, if you take n equals 3. So the stereographic projection in this case is exactly this one. And we have to look at the O2 times O2 orbit of a point in the sphere, for example, this one. Then I will have to make all the rotations, well, all the possible elements here that have the same norm and all the possible elements here that have the same norm. I will end up having this orbit. So now I can take the stereographic projection of the orbit and see how this looks in R3 to try to see how the orbits of one point look in the Euclidean space, and they look like tori. So if we had a sign-changing solution that has, for example, 3 zeros, the solution in R3 would look like this. It would be, for example, positive inside the torus, the green torus, the negative in the space between the green torus and the orange torus, the negative again between the orange and the blue and the boundary of these two torus, and then a negative again outside, or positive, so positive, negative, yeah. So this is how nodal lines, nodal surfaces look like for this construction, for these solutions with these symmetries. So we have now more or less have an idea of what it means to have a nodal solution of the Yamabe problem. But what else can we say? So is there a way of characterizing these surfaces? Why are they at these exact points or not different sets? So this is where optimal partitions and species fighting will come in. We will try to see that these nodal surfaces will optimize, in a sense, the space. We'll make an optimal partition. So let me consider now this objective. Split the sphere in disjoint subsets that satisfy some optimality condition. This is what we are going to try now as an optimal partition problem for the sphere. Okay, what would be this criteria for optimization? Is going to be the following. Consider a subset of the sphere, and in this subset, in this open subset, consider this PDE, which is the Yamabe problem with Dirichlet boundary conditions on the boundary of this set U. And I ask also for the symmetry. Okay, for a solution of this problem, which we now know it exists because of the compact embedding, I can associate a cost function. So the cost of U is going to be the infimum of the L2 star norm of all the solutions of the problem multiplied by a factor. This is one way of defining a cost. Once I have a cost, I can define an optimal partition problem. So now I look at the set of all subsets.
What about
I am discarding this here. I want non-trivial solutions. So the set of all possible partitions are going to be the set of all sets different from the empty set, which have the symmetry, are open in the sphere, and are disjoint. I'm not asking them to fully cover the sphere, but we are going to get this for free during the process. But so the idea is how many parts can I split the sphere so that the parts have the symmetry and they are disjoint. And I want a partition that minimizes all the costs of every piece in the partition. Well, let's see if we can solve this problem. It turns out that solving this kind of optimal partition problems is very hard, even with the symmetries. So to find a solution of this problem and to link it with the Yamabe problem, we're going to use competing species. So I have here a numerical simulation.
Go back to the so you're partitioning into a finite, so there's these joints and you're using them.
M is fixed. So for each M,
Over a fixed partition.
Yeah.
You're not trying to
on the set of partitions, but the M is fixed.
No, but it's fixing M, right?
It's fixing M, yeah. So
Then you're doing partitions of only M
exactly.
subsets, and you're doing infimum over partitions with M subsets. You're not doing partitions over M.
No. So once I fix M, so for example, I would solve the 2 optimal partition, the 3 optimal partition, the 5 optimal partition. Probably from everything, the one that has the least energy is the sphere. Yeah. Okay.
What you're saying is that in the end, for a fixed angle breaks up into a covering edge.
Exactly. And we want the optimal, it's a covering, and it will have a relationship with the nodal solutions of the Yamabe problem. Exactly. So as I was saying, to understand this idea of why we're going to use competing systems, I have here some numerical approximations of the solution, but I am a little bit afraid of using them because my laptop has been having problems lately. So I will explain this with other words, and in the end of the seminar, we try this. So why are we trying to use competing species? Well, there are systems for competing species looking like this. So what do we have here? This is a Lotka-Volterra system. And here I'm using the evolution problem. So now we have time, and this is like a growth rate. This is a diffusion term. This is going to be a birth rate. So U and B are density functions for 2 different species. This is a concentration term because, well, if I have too many wolves in one side, they will start dying because there is not enough food. And they are also fighting between them. Here, lambda is a positive parameter. Now, the thing is that if lambda is very large, and I take the time go to infinity, they will segregate. No, they don't get any advantage of living together. So after a while, they will try to. So we have Dirichlet boundary conditions. They will try to minimize the interaction. No? So they will try to segregate. The larger the lambda, the smaller, the more clear the segregation is. So, well, we're going to use this idea that when lambda, which is the competition parameter, is very large, these 2 populations segregate. But other than this lambda parameter, they pretty much have the same capabilities of fighting. No, they have the same diffusion coefficient. They have the same birth diffusion. So when they segregate, they will try to optimize also the space that they are using. No, there is not advantage of one species over the other. So we're going to use this idea of segregation of competing species. Now, this system here is not variational. Even if I remove the time derivative, what I get is not going to be variational. So in order to make it variational, I just put here some suitable powers, and I put here a power that relates now the system with the Yamabe problem. The idea is more or less the same. I mean, this is going to be, again, a competing system. And when lambda goes to infinity, I will also get a segregation phenomena that I will use now to try to link nodal solutions to the Yamabe problem and optimal partitions. Okay, so now consider this system. It's a system of M components, M fixed. And I'm going to, so this first part is just the Yamabe problem. And now I am adding this second part telling me how UI and UJ couple, no? Okay, this system here has a variational structure, meaning that I can associate it, an energy functional and critical points of this functional are going to be solutions. The existence of solution was guaranteed by Monica Clapp and Jay Sulkin in 2019 using something called the Nehari manifold approach. So now this is the theorem that puts everything together. For each lambda, there is going to be a least energy solution of the system that depends on lambda and on m. When lambda goes to infinity, these least energy solutions will converge to a limiting profile in the norm of H1G, which is this Sobolev space that we constructed to give a meaning to the energy functional. Each limiting profile is non-negative, is continuous, and if I restrict the profile to its support, so the set where the limiting profile is positive, then what I have is a least energy solution of the problem in the support. So as we were expecting, this the competition term will go to 0. Well, this happens for the Lotka-Volterra, and here I just need to put the right exponents. Something like this. This type of terms will always go to 0 as lambda goes to infinity. Okay, so moreover, when I look at the supports of each of the components, they will belong to the set of possible partitions because we were always considering that the symmetric setting, and they will actually solve the optimal partition. So this intuition that we developed before, that species that have the same fighting abilities really optimize their territory, well, it's reflected now here. They will be a solution of the optimal partition problem for each M fixed. And now finally, if I take all the limiting profiles and I alternate the signs, then I will recover a nodal solution of the Yamabe problem. So one of the Ding solutions, but now we really know much more about the solution. We know how many nodal regions it has, and we know that each of the nodal sets optimize the space in some sense, in some very precise sense, with a very precise cost function. Yeah. Yep. So if we had,
so you start I don't see where the partition comes from.
So here you have two species fighting in the whole of the sphere. But now you let lambda go to infinity. So they are really, really fighting against them. The only way they can survive is if each of them go to different parts of the sphere at the limit. A lot of them, yes, so here we have it, no? In the limit, it will be 0 here and positive here. This would be like the one of the profiles, and the other one will be 0 here and positive here. It's not clear, but it requires a proof. Yeah. So once you use the energy approach with an Nehari manifold, you can show that this always has a minimizer, and the minimizer can be taken to be positive, yeah, or non-negative. Non-negative and non-trivial. Yeah.
So the variance for gamma, this reduces always to a 1D problem.
Yes, well.
And that's why you can order
exactly
components so that you can do the assumption.
We're using strongly the symmetry in order to have this construction here. Otherwise, it's not clear.
Three of them.
And then you're screwed, yes. But here we can because of the symmetries. So
see that Q is really a function of the sphere, because at the end points of the intervals, the finite interval, right, the P parameter, needs to have some conditions.
So
I mean, if you do the stereographic projection, it's not a finite interval.
right.
You have some symptotic condition and some condition that's zero.
You have integrability. So you go from H1 from the sphere to D1.
Maybe
well, in the way you can go from energy solutions to energy solutions, you always have decay at infinity. And in fact, how do optimal partitions of Rn look like? What they look like tori, no? So now we will.
What about the zeros? Because the user just the positive part of the solution, right? So they're open sets.
Yep, they continues.
And I suppose, if I mentioned correctly, that they just touch at zero at the boundary, but I mean, is it clear? Or they just sort of come down like compactly supported and have a sort of a
Here, you mean? So you can show that in the limit they are really solutions, no? You do this by an energy approach. So
have like regions where all of them are zero? Right?
no. Well, okay, here if you want. But once you have a support, once you have the limiting profile and you have the support of the function, you can show that in the support, you are a solution of an elliptic problem. And because of this, so you're a solution. The limiting profiles are a solution of an elliptic problem, and then you enjoy all the properties there. Okay, so optimal partitions of Rn look like something splitted by tori. And well, this approach was started by a paper by Conti, Terracini, Versini in 2002, where they explored the relationship between two optimal partition problems. So the optimal partition between two sets, two equations, and nodal solutions in the subcritical case. So not with the critical exponent, but anything below. And then there are a group working with these techniques and systems, and particularly Hugo has worked a lot on this. Then there are also papers working with the critical case and two sets to optimize the partition. Then there have also been papers considering other operators like polyharmonic operators, papers working on more general manifolds and not just the sphere, and papers working with more general symmetries. Okay, so before we go, I want to talk about two more results relating to Schrödinger systems. So not exactly linked to what we have talked yet up to now, but related somehow, because now we are going to consider the Schrödinger system on a ball or a domain. We have here the same type of coupling. So my betas are going to be taken positive for the same species and negative for different species. So they are competing for resources. And I am adding here an epsilon. So these kind of problems are called singularly perturbed problems. And I'm not taking now the critical exponent, but subcritical exponents. And the question I want to answer now is, how many positive solutions does a system like this have? Where B, well, we can think it of a ball to fix ideas. Okay, so to have an idea, maybe we can look first at the equation. So if we look at the equation without any interaction with any other components, this turns out to have a unique positive solution, and the epsilon plays no role in it. So for any epsilon and for any exponent here that is subcritical, this problem will have a unique positive solution. And it looks more or less like this. So if the epsilon is very small, the solution tend to concentrate. And this was shown in a series of papers. So in view of this result, can we expect that the system will have perhaps only one positive solution? Well, there is also this result by Wang, Wu, and Liu that tells us that there are at least two positive solutions if we consider a system of two equations. So actually, they make a numerical analysis of the solutions, and they really look like these two pictures. So this one is called the sphere packing position, because the concentration peaks for epsilon very small look like they are also optimizing the distance between them and the distance to the boundary. Okay, so this is one of the positive solutions. This is the solution that has least energy. And then we also have this other solution with two peaks closer together, but more concentrated. The height of these two solutions is higher than these two here. Okay, we have at least two.
But you can also rotate them.
You can also rotate them, yes, up to rotations. Yeah. So what about the general case? If you have L equations, can you have L positive solutions up to rotations? And what we showed is that this is the case. So when epsilon is small enough, if we have L positive solutions, then the system will have at least, if you have L equations, then the system will have at least L positive solutions. And we show this with an Nehari manifold approach, Lusternik-Schneiderman theory, and we used configuration spaces. And the last result I want to talk to you about is, well, what about another property of this system, which is the decay at infinity? We know that a solution of this system, which now we are considering in Rn, but is still sublinear, it belongs to an energy space, so to a Sobolev space that has some integrability condition. Can we say something about the decay of these components? Well, again, let's look first at the equation. If we look at this equation, well, this is the Schrödinger operator. It's a nonlinear Schrödinger equation, and it's known that it has an exponential decay. So could it be that the equation always has exponential decay? Well, the thing is that no, in general, all solutions of the Schrödinger equation will have exponential decay. So could it be also that all solutions of the system will have exponential decay? The problem is that in the interaction, there will appear terms like this. And we are assuming that P is between 1 and 2 star over 2. 2 star was the Sobolev critical exponent, which, okay, I erased, but it's this one. So when n is larger than 5 or equal to 4, then this is 1. And then we have what it's called a sublinear power, because now this P minus 2 is negative. No? And of course, it's multiplied by the U1, but all in all is going to have a sublinear power. We have this term here. Yeah, so you could say necessarily it has to have exponential decay, but let's be careful with nonlinear terms, with sublinear terms, because we have here an example of what are the pathologies in the sublinear world. Imagine that you have a function which is C2, which is positive, and that behaves like a power outside a ball of radius 1. So it doesn't matter what it's doing in the ball of radius 1, but outside it decays as a power. And here it can do anything. But I want it to be positive and I want it to be C2. Well, in one dimension, we were thinking this in R, just to show the pathologies that sublinear terms can produce. This function here is going to be in the right energy space, and it's going to solve this equation where I can take a coefficient C defined like this. So exactly what I need in order to get equality. And this coefficient defined like this is going to go to 0 as x goes to infinity. So exactly the setting that I have here, because this coefficient here is also going to 0 because it belongs to an energy space. And what I am left with is the sublinear power. So here we have an example that sublinear powers could be delicate. We're in between now. We don't know if it's going to be a power law decay or exponential decay, or maybe in some cases and in some cases. Well, we have this theorem telling us that there is always exponential decay. So for this system here, you always get, doesn't matter if you're positive or sign changing, you always decay as an exponential. If you are positive, then the decay is optimal. And in fact, we did it a little bit more general. If we consider here different potentials, that are Hölder continuous, bounded, and bounded away from zero outside a large pole, then it can happen that each component has different decays, where the mu I is between 0 and square root of sigma I, and sigma I relates to this infimum of Vi at infinity. Okay.
Ask a question?
Yeah.
So now that you have this decay, and do you remember that we used once paper by sharp again? Can you prove that this is sharp? So from above and from below?
For positive solutions, yes. Yes.
Then
Yes.
it's sharp.
Yes, yes. Unfortunately, we cannot argue uniqueness now because it's a different type of system. But you can be sharp. For positive solutions, you can make a sandwich above and below. Yeah. And with this, I finish my seminar. Thank you very much. And these are the 3 papers I discussed today.